Okay, so we've been talking about gravity and force and even some energy going on, and I want to continue that discussion. Okay? We're going to look at what happens when energy is not conserved. You know, we did mechanical energy, which is gravitational potential energy plus kinetic energy plus elastic energy, and we had all that mechanical energy. But occasionally we said mechanical energy isn't conserved. Okay? Sometimes friction does work. Okay? And if friction does work, then we lose mechanical energy. And so I want to take a look at what happens to that. Okay? So consider just the classic case. Say there's an 800 kilogram car, it's a nice small compact car, 800 kilogram car, traveling at 8 meters per second. Maybe even whatever, 8 meters per second, that's fine. It stops. Okay, I want to know a couple things. How much work does the brake do? How much work do the brakes do? And where's the energy? Okay? Because we had something go from moving to not moving, so it lost kinetic energy. It didn't go up a hill, so it didn't gain potential energy. It didn't compress a spring, so it didn't get elastic potential energy. It just stopped. So we know it started with some kinetic energy. Kinetic energy is 1/2 mv squared, which in this case would be 1/2 400. 1/2 400. Wow. Okay, so I can't even calculate energy today. That would be 1/2 800, which is 400, times v, which is 8 squared. So I've got 64 times 4, which is 25600, right? So I've got 25,600 joules of kinetic energy to start. It doesn't matter how much force the brakes exert. It doesn't matter what distance this acts over. At the end of the day, the car is stopped. Kinetic energy equals 0. Okay, that means we lost the change in kinetic energy is negative 25,600 joules. Okay. Yikes. Where did it go? Because the law of conservation of energy doesn't say that it's okay to lose energy. It says energy is always conserved. So where did it go? How can we deal with this? Well, the brakes did negative work. The brakes did negative 25,600 joules of work, and they converted it into another form of energy called thermal energy. Okay? You guys are familiar with this concept already. You rub your hands together, they get warm. So they're taking in the kinetic energy from the motion and converting it, the friction converts it into thermal energy. Okay? And so our day-to-day understanding of thermal energy isn't really that great, but we would measure this loss of kinetic energy as an increase in temperature. Okay? And so we don't actually measure thermal energy in temperature, but we'd measure the increase in thermal energy by looking at temperature. Okay? And so what actually happened to this energy is that it became heat, essentially. Kinetic energy became heat. Now that's really an interesting thing, because it took years and years and years and years of study and debate before scientists really even came to understand that making something warmer is the same thing as doing work to it. And in fact, the reason the unit of energy is called the joule is because James Prescott Joule, who was actually a brewer, right, who was interested in making beer, he was the one who did so much work and actually came to the conclusion that yes, actually heat is a form of energy. Heat is that same stuff that allows us to do work. So when we increase the temperature of something, we've increased the energy of it. For years and years and years before that, there was the policies and the ideas of Antoine Lavoisier, who basically said heat is a substance that flows from warmer objects into cooler objects, and they thought it was a mysterious fluid called caloric. Okay? And so the calorie that we use today to measure the energy content of foods is actually a remnant of that bad idea, that bad theory that heat is caloric and it's something that an object possesses or doesn't, and you can transfer it from one object into another. Today, though, we understand a very different type of world, and so really to understand temperature, we need to back all the way up to atomic theory, and kinetic theory. Okay? Now, you guys have all taken chemistry. You all are aware of atoms, right? An atom is the smallest part of matter, and atoms are made of protons, neutrons, and electrons, and woo. Okay? But the cool thing about atomic theory is it says atoms are in constant random motion, always moving. Okay? They never, ever, ever, ever stop. Now, for the most part, we don't see this motion, right? Especially in solids, and we see it a little more in liquids, and we see it a lot more in gases. Okay? Atoms are always moving, even in solids. Okay? Now, you got to stop and think about this, because we take for granted sometimes, okay, yes, everything's made out of atoms, but we don't really think about what's actually happening with atoms. Atoms like each other, but at the same time, atoms don't like each other, right? At the center of every atom is the nucleus, and the nucleus has a positive charge, and it's made up of multiple positive charges, except for hydrogen, which only has the one, right? So these protons are in here, and the reason there's any electrons out around them at all is because the electrons are negative, and so negatively charged electrons are attracted to the positively charged nucleus, and they hang out together. Okay? Now, a bond that forms really forms because there's an electron right here on the outside of this atom. Well, this nucleus is attracted to it, but another nucleus over here is also attracted to it. So this mutual attraction for these electrons in the middle holds atoms together. That's basically what, in a simple kind of form, that is what a chemical bond is. So atoms are always moving, but we've got to pay attention to some other things. Atoms have forces between them. Okay? Atoms have attractive forces between them. And the reason there's attractive forces is because of the opposite charges. Okay? Electrons and protons want to get together. Okay? So these opposite charges try to pull the nuclei of different atoms together and hold them there. Okay? And in solids, that's a pretty strong force of attraction. Strong attractive forces. And so what happens is instead of the atoms bouncing all over the place, they are still moving, but they're not moving as far. Okay, so you can imagine solids as the atoms, the forces holding them together as little springs. So you get a crystalline structure where you have all these little atoms, and yes, they can move, but instead of freely moving, their degrees of freedom are limited because they can only move in certain directions and into certain places, but they always end up coming back to the same point. So in a solid, the atoms oscillate, they say, around one point. So this thing could vibrate over here, and it could come this way, and it could come this way, and it could come this way. But the further it gets this way, the more this side pulls back on it. Okay? So solids have strong attractive forces, and that doesn't mean that the atoms don't move, but the atoms oscillate around a fixed location. Atoms oscillate around a fixed location. Okay? So they can still move, but not out of position. Okay? And this is what gives rise to a lot of the properties of solids, right? Solids have a definite shape, so you can't really compress them, and they have a definite volume. Okay? They don't change either of these properties when you move them from one container to another. They always basically look like this. Okay? And this is called a crystalline structure, and different atoms arrange themselves differently, but they're there. Now, why doesn't this structure actually get closer together? Well, not all forces between atoms and molecules are attractive. Atoms also have repulsive forces. Okay? And for exactly the same reason, atoms have repulsive forces between them because electrons don't like each other, protons don't like each other, right? In the middle of the atom, we have the positive nucleus, these two nuclei, they don't like each other. They don't want to get together, right? So even though there's some electrons in between, the closer and closer these things get, the more and more they start to push away from each other. And when you start squishing electrons together like that, the electrons don't like each other. So atoms have repulsive charges or repulsive forces because similar charges repel. Okay? And so the other states of matter, it's sort of this balancing act. Okay? What's stronger? Is it the attractive forces between the atoms, or is it the repulsive charges between the atoms? And liquids are sort of your intermediate, right? Liquids, the atoms slide past each other. Okay? They're still really, really close. They still don't like to get far apart from each other. But there's nothing that says they can't move. So instead of, springs holding them together, they will slide around and move past each other. Okay? And so there's no definite shape, but there is a definite volume. Okay? They can't be compressed. Whoops. There is a definite volume. They can't be compressed. Okay? They're already really close together. They don't want to get any closer together. They don't really want to move apart. The attractive forces are strong enough to hold them close, but not so strong that they can only have one position. And then, of course, there's gases. Now, gases are probably the easiest to study as far as atomic structure goes because they actually are pretty much apart. Very, very weak forces holding them together, weak attractions. Okay? Gases tend to be big, heavy atoms that don't need to bond or pair. Oxygen, O2, it becomes stable because there's these two electrons that are these two electron pairs that are shared between them, and so now both these oxygen nuclei get to share those electrons. They both get to a stable electron configuration, and they don't really need to share with anybody else. They're not interested in that, and so they don't attract to other molecules very well, or other atoms very well. Okay, so there's weak attractions and very high speeds. Okay, and what this means is these things can move around, and the atoms do accelerate all over the place and bounce off of things and do different things. So high speeds, weak attractions, and big gaps. Okay, which means you can compress a gas, you can make it slow down, you can make it speed up, and you can also make it occupy less space. I mean, that's basically what a tire is, right? We take atmospheric air and we compress it down into a small little closed container of our tire and increase the pressure. All right, so let's talk about that a little bit. Okay, pressure of a gas. And fluids, all fluids have a pressure. So fluids are gases or liquids. Fluids are things that can flow. But if we think about pressure of a gas, okay, a contained gas, like inside a balloon or a tire or something, all these little atoms are in here buzzing around, and they don't really like each other very much, and they have a little bit of energy, and so they collide with each other, but they don't stick, they don't like, so they bounce off. They collide with the walls, then so that right there, that's a force exerted on the container of the wall. And because of that, there's a pressure. Okay, so pressure is due to collisions. Pressure is due to particle motion and collisions. Okay. And so the faster the particles move, or the more the particles move, or the harder they hit the walls, or the more particles we put in here, the more and more and more and more collisions we get, and so the more and more pressure we have. So pressure is due to particle motion and collisions, and essentially what it is it's force distributed over area. Okay? Force over area equals pressure. Okay? And so you can apply the same amount of pressure with a big force or a small force by changing the area. That's why when they say you're walking on thin ice, you should lay down and spread out your weight over a larger area because it reduces pressure. Similarly, the reason we use sharp pointing needles and knives instead of dull blades to puncture things is because you can use a small force over a small area and get a big pressure out of it. So it's easier to slice through things when you have that smaller area because it doesn't take as much force to push your way through it. okay, because you've increased pressure. Now, there are units for these things, right? Force is measured in newtons, area is measured in square meters, and together that's called a Pascal, okay, for Blaise Pascal, who did some work with gases and pressures and fluids and stuff, okay? And the abbreviation for Pascal is capital P lowercase a. A newton per square meter is not very much pressure, okay? A newton weighs about a quarter pound on Earth, okay? Well, newton is about a quarter pound. They measure the same thing. Square meter is, you know, if you take about 3 tile by 3 tile square of the floor, you're looking at a square meter. So if you take a quarter pound and spread it out over a square meter, you are not looking at very much pressure. So we are going to use kilopascals, 1,000 pascals. Okay? And atmospheric pressure, the air pushing down on you, is right around 90 to 100 kilopascals. Okay? So we have this pressure, we measure it in pascals, and we are going to try to manipulate it. Okay? But one of the things we can do to do that is we can try to mess with the particle motion. And so back to that car problem at the beginning, we said that the brakes do negative work and convert mechanical energy into thermal energy, and we measure that as an increase in temperature. Okay, so how do we measure temperature? I mean, we've got a couple scales that we're familiar with. We can measure it in degrees Celsius. We can measure it in degrees Fahrenheit. Okay. Well, where did these come from, and how do they work? Well, the reason we can measure temperature is because temperature affects a lot of different things. In our day-to-day life, we think of temperature as how hot or cold something is, which is perfectly fine. Okay. But how do we measure it? I mean, if you think about a glass thermometer filled with a liquid, okay, as it gets warmer, this liquid gets up and up and up and up and up and up, higher and higher and higher and higher and higher. And that's how our thermometer works. And we measure this change in height or volume of a liquid in order to measure a temperature. Okay, so that's one of the things we keep in mind. Temperature affects a lot of things. Okay, temp affects anything from color, right? You know, if you get a piece of steel warm, it changes color, it starts to glow. It affects size. Generally speaking, warmer things expand, okay? And that's what's going on in this thermometer over here. As you get the alcohol in here warmer and warmer, it occupies more and more and more space. If it's a mercury thermometer, it does the same thing. Okay? So size, warmer objects generally expand. Water has a notable exception in that when it gets below 4 degrees Celsius, it actually starts to expand again. So, ice floats because water expands when it gets colder, and that's a little bit weird. But warmer objects usually expand. Okay, so that's a property we take advantage of. When I say color, okay, we said glowing. Resistance. Okay, now this is an electrical property, and so if you use an electrical temperature sensor, basically the warmer and warmer particles get, the less able they are to conduct electricity, and we can measure that change in resistance and relate it to the temperature. But that still doesn't explain why we have different scales or how these actually work. Okay, really, it's arbitrary. Okay, they just pick 2 points that are easy to create. Okay, and so 2 points that are very, very easy to create for the Celsius scale, and the way it was based was water, because everybody can freeze water, everybody can boil water. So we can freeze and we can boil, and so those are the two temperatures that are easy to reproduce, easy for everybody to get, so that the scale can be common for everybody. And so actually Celsius, when he designed the scale, he put 100 degrees at freezing and 0 degrees at boiling, and somebody else came along and said, let's do that a different way. So we have 0 degrees Celsius is when water freezes, and we have 100 degrees Celsius is when water boils. So those 2 points were assigned just arbitrarily. We picked a liquid that's easy, everybody has access to, divided up the temperature range from freezing point to boiling point as 100 different divisions, and called each one of those a degree Celsius. Okay. Now, what's weird about that is we defined this range of temperature. We said there's 100 divisions here, but we can use it in both directions, right? So when we get a negative temperature, what does that actually mean? It just means below freezing point, right? Below freezing point. Similarly, above 100 degrees, this isn't an absolute maximum. This just tells us that's the temperature water boils. If you get above 100 degrees, that's above the boiling point of water. This is below freezing point of water. Okay? So this was the Celsius scale. So between 0 and 100 degrees, 0 and 100 is 100 degrees, 100 divisions, and so every step on here has the same change in temperature. Okay? And so we can measure that by looking at how a fluid moves through there or whatever. The Fahrenheit scale was done a little bit differently. 0 degrees was water with antifreeze. I don't know why Lord Fahrenheit did that. And 100 degrees, okay, his arbitrary, so this was antifreeze, right? 100 degrees was actually his human temperature, okay? And we know today that this is shifted a little bit. It's not 100 degrees, but he was actually measuring the temperature of a person and averaged that. And he said, okay, so antifreeze water 0 degrees, human temperature is 100 degrees. That's my two arbitrary points, and I'm going to divide up my scale. Now, Fahrenheit was actually the first one who made a standard scale and was able to make thermometers that everybody could use because they measured in the same way. So that's why his scale stuck and people used it. Not necessarily because his beginning and ending points made sense. Okay? Today we define it a little bit differently. Today we say, okay, 32 degrees is the freezing point of water, 212 degrees is the boiling point of water, and so we can divide this up the same way that Celsius divided his scale up, except the difference is there are 180 divisions between freezing and boiling, and so 180 degrees, and you can actually have temperatures from 0 to 32 that are positive still, but water is ice. Okay? So below freezing point of water is negative here, below freezing point of water is below 32 over here. So both of these scales actually measure in the same way and do the same thing. It's just that the 2 points that we picked were different and they were arbitrary, and so it doesn't really matter. And so a lot of times people are like, well, you can't convert from Fahrenheit to Celsius, they measure different. Well, that's not true. Okay, if you look at it, there's 180 divisions between boiling and freezing on Fahrenheit scale. There's 100 on the Celsius scale. Okay, so 100 degrees Celsius equals a change of, I should say that, a change of 100 degrees Celsius is equal to a change of 180 degrees Fahrenheit. So the ratio of 1 degree Celsius to 1 degree Fahrenheit, if we divide by 180 degrees, divide by 180 degrees, okay, we get the ratio of Celsius to Fahrenheit is 5/9 of a degree. So 5/9 of a degree Celsius equals 1 degree Fahrenheit. Okay, that's a conversion factor. 5/9 of a degree Celsius equals 1 degree Fahrenheit. Okay, a degree Fahrenheit is actually smaller than a degree Celsius, so it's actually a little bit more precise of a scale, at least until we start getting into divisions. Now, the other thing that you got to keep in mind is, where does 0 start? Okay, 0 on the Celsius scale starts at freezing point of water, but the freezing point of water on the Fahrenheit scale is 32. So 0 degrees Celsius is equal to 32 degrees Fahrenheit. Okay, and if I add 1 degree Celsius, 0 degrees Celsius, or whatever, plus 1 degree Celsius here, okay, then I have to start with 32 degrees over here and add on not 1 degree, but the inverse of this, 9/5 of a degree Fahrenheit, 9/5 degrees Fahrenheit. Okay, and so we can convert between these two. We just say the temperature in degrees Celsius is equal to, or I guess in degrees Fahrenheit, depends on which way you're trying to use it. The temperature in degrees Fahrenheit is equal to the Celsius temperature times 9/5 plus 32. Okay? So if I have 0 degrees Celsius, I have 32 degrees Fahrenheit. So, man, that's messy. Temperature in Fahrenheit is equal to the temperature in Celsius times 9/5 plus 32. If I have, and of course this works the other way around as well. So let me write this out one more time. Fahrenheit equals degrees Fahrenheit equals degrees Celsius times 9/5. Okay, that's because of the difference in size of the degree, plus 32, and that's because of the difference in 0 points. Or you can say degrees Celsius, and now you got to be careful, we're solving this the other way, equals degrees Fahrenheit minus 32, right? And then you've got to multiply that by 5/9. We just solved this equation for C instead of F. Okay, so that means there's actually a point where degrees Celsius and degrees Fahrenheit are the same. They have the same temperature at the same value, and that's a fun exercise. I'll let you figure that one out. But these two temperatures you can convert between them. It's not a simple thing, but remember the 32 is because the freezing points are different, and the 5/9 or 9/5 is because the size of each change is different. Okay, so temperature is used to measure thermal energy. We also need some other tools to do that, and it's measured in degrees Celsius or degrees Fahrenheit, and it's also related to pressure. And we're going to do a lab where we see the relationship between pressure and temperature, and we're going to try to come up with a scale that makes sense, because right now you can have a negative temperature, and that tells us it's below a certain point. Okay, but is there an absolute maximum or an absolute minimum on the temperature scale? And that's a question that deserves some investigation.